Okay. So, the table I gave you is right out of your lab. It's called an activity chart or activity series. What that means is it's really a chart on stability. The higher in the chart, the more stable it is. The lower, less stable. Now, there's a phenomenon going on here called oxidation, and you've never heard of that before from a chemistry class. You've heard of oxidation, though. The opposite of oxidation is reduction. And you probably have not heard of reduction, but of oxidation. They go hand in hand. One cannot be without the other, no exceptions. So what is oxidation? Oxidation is loss of electrons. When something, yeah. Is it?
Yeah.
Oh, okay. So Friday Lab people, you have Friday Lab? Okay. Tell me in lab and I'll change it. Don't worry about due dates. I can change that in seconds, so don't worry. Huh? Yeah, it's a wet lab though, and on single replacement reactions. And that's why I'm talking about in lecture today, single replacement reaction. Does that make sense? Okay. All right. So oxidation. Now, this is a big topic. In your next chemistry class, you're going to spend a lot of time on oxidation reduction. Now, oxidation reduction is a mouthful, so everyone abbreviates it to redox. The re is reduction, the ox is oxidation. So we're talking about redox reactions. Now, that's one type of reaction. I briefly mentioned neutralization reactions. Next Friday is your next lab on double replacement reaction. That's the next type of reaction. And there's a couple more that we'll talk about. Okay, so when we talk about oxidation and reduction, there's a concept called a half reaction. Because we always have a reduction going on at the same time as an oxidation. So that's why we say, well, there's a half reaction and the two halves equal a whole. Okay, so let's talk about the half reaction for oxidation. Okay, oxidation again is transfer of electrons. Electrons leave the reactant side, the left side, go to the right side. So anything on the right side is leaving. Anything on the left side is coming in. Okay, so this is like a baseball game between the pitcher and the catcher. When the pitcher throws the ball, the idea is for the catcher to catch the ball. Everything goes right. So in a redox situation, oxidation is giving up electrons and something's got to be there to receive them. No exceptions, because anytime we have a stray electron, that's called a free radical. Free radicals are extremely unstable, and because of that, they react to the first thing they see. Nuclear explosion, Chernobyl's reactor explosion back in the 80s. Lots and lots of free radicals. A lot of people died because of that. So ionizing radiation, gamma radiation is same as free radicals. So if we have a free radical and a common oxidation reaction, we don't want it just flying off willy-nilly. We want something there to receive it. So we always have an oxidation and a reduction reaction going on at the same time. And I can't emphasize this enough. Okay, now the problem is with oxidation reduction, two half reactions, and they're very simple reactions, but there's a key element that has to agree. When we throw out an electron, we're going to have something to receive it. If we throw out one electron, but the recipient wants two electrons, well, then that means the one who throws it out has to do it twice. So what I'm saying is electrons leaving must equal electrons receiving. It's kind of like we balanced equation. Now, we're going to algebraically move these two together. When we move them together, the electrons have to be equal. 2 given off, 2 received. 5 given off, 5 received. No exceptions to that. So we're going to add these algebraically. What's going to happen is, notice the electrons cancel. They've got to cancel because you can't have any stray electrons. So that means the top one, we've got to multiply by 2 all the way through. That means we got two starting silver metals. Remember, the superscript 0 means it's a metal. Gives 2 silver cations, pluses, plus 2 electrons. Now notice 2 minuses, 2 pluses equals 0. 0 on the left. Okay, and conversely, if we are receiving 2 electrons, so we've got the iron ion is receiving 2 electrons. When an iron cation plus 2 receives 2 electrons, it becomes iron metal. This is how they make steel in a blast furnace, moving electrons around. Okay, so when we add this up, we've got the electrons cancel, so we end up with 2 silver metals plus 1 iron cation, a plus 2, yields 2 silvers, ion, and an iron metal. Now, question is this reaction going to happen? Now, there's 2 ways to answer that question. For us, it's going to be the activity table. When you get into 2B, you're going to talk about something called electron volt values. And that's what the activity table is based on. And that's all you're going to hear from me about EV values, okay? We're going to be looking at activity charts, activity tables, and you're going to generate one in your lab this week. Okay, so this is the way to do it. We have now single replacement reactions, all but one exception involve metals. It's always a metal reaction going on. Metals receive and give up electrons very easily. Frequently, that's why they're always involved in single replacement reactions. Except for hydrogen, H2 gas, and H plus ion. And you'll see that in your activity chart. Okay, so is this reaction going to happen? So we find the 2 metals and the reaction in the activity chart. Let's see, where is it now? Where did it go? Here it is here. So let me okay, so what we're going to do is we're going to find silver and iron. Oops, iron. Where's iron? Okay, so we go to our reaction. Find the silver. Excuse me, we find the metal, the one with the 0 superscript. Okay, which is going to be this guy here. Question is is this guy above the iron? Is the silver metal above the iron ion? No, it's not. So this reaction is a no-go. Now, this is a table of metals, except for the H2, metals being oxidized. Remember, I mentioned a little while ago, whenever you have oxidation, we have to have a reduction to go along with it. So the higher in the reaction table, the more the tendency is to oxidize. Yeah.
Can it be written?
Sure. Life is like that.
But it possible reaction.
Yeah, exactly. So if we started with the iron metal rather than the silver metal, it would go. So the question is, burn this in your mind. If the metal, one with 0 superscript, is higher, it goes. Because it wants to oxidize more than the other. So the blue X is there because the silver is not above the iron. The iron wants to oxidize more than the silver, and it's already oxidized, +2. Okay, so does that make sense? So basically, most single replacement reactions are this here. We've got a metal and a salt, and then that gives us, this is also the salt, gives us a salt and a metal only flip-flopped. When I say salt, that's a very generic term in physics and chemistry, not table salt. Table salt is a member of that. But when I say salt, from a chemical perspective, that's ions, ionic things. It could be calcium hydroxide, it could be strontium hydroxide, it could be uranium hexafluoride, it could be sodium chloride, not just sodium chloride, okay? So salt means we're talking about ionic stuff. And we're going to see with double replacement reactions, we're only dealing with ionic stuff. Okay, so single replacement reactions involve a metal, except for H2, a metal in its oxidized state, which is going to be the plus whatever. Yeah. Exactly. So whatever you start with has to be higher. Kind of like life in when you're meditating, a higher state. Sorry. Okay. So basically, this is the rule. Find the two elements in the activity chart. In the middle, on the left, has to be higher than the other one. Now, sometimes textbooks will leave off a little superscript 0. If there's nothing up there, that means it's 0. That means it's a metal. I strive to always put it in to make sure to differentiate it from an ion. Also, when we get to next Friday, we're gonna start filling in little S's down here. Guess what S stands for? Solid. So it could be solid, liquid, or gas. Okay, for single replacement, it's always an S, except for H2, which is gas. It's the only one. Okay. Now you can't have a cation without an accompanying anion to go with it. No isolated charges are allowed in nature because of stability issues. Very, very unstable. So we have always have an accompanying anion to go with the oxidized metal. So in this reaction here, we've got the metal is aluminum. In fact, let's clean this up and go through the steps here. Do you? Okay. So this would be a typical question. Can I take aluminum metal and throw some ferric sulfate in there? Does anyone know a use for ferric sulfate medically? Like when you go to the dentist or your pet groomer cuts the fingernails too close. Anyone know what they use ferric sulfate for? Exactly. Blood, it clots blood really well, and it's cheap too. So I recommend having that at home. My groomer has a little, she not only has a packet, she's got a bottle of this stuff. And she never tells me there's been an incident. My older dog, this is an aside, sorry. My older dog is 14 and he's 2 years past, and so the vet says he's in great shape, but he's got sebaceous cysts. Who knows what a sebaceous cyst is? Anyone? It's the most common type of tumor. It grows out of the sebaceous gland, which is where sweat comes from. And so he's got a number of them, and they're three-dimensional. And so when the groomer's, grooming him, occasionally she'll nip and it bleeds. So she has her vial of ferric sulfate out whenever she grooms my older dog. He's in really good shape though. Hip dysplasia, 0. His weight's really good, and he's got a wonderful disposition, but he's got cataracts and he doesn't hear worth a darn. Kind of like me. Hearing part, I don't have cataracts though. Okay, so ferric sulfate. Okay, we take aluminum metal and throw in some ferric sulfate. Does anything happen? Okay, so I'm going to do the half reactions. Now, your lab doesn't have you do half reactions, but I think it's nice with half reactions because that's really what's going on. So let's take the aluminum first. Okay, metals go to salts. So the aluminum salt is a +3. How do you know that? You look on your table. Now, when we get to naming, nomenclature, I'm going to give you a common ion chart. And there'll be a whole bunch of ions on there, and you're not required to memorize them till you get to your next class. Some of your teachers will have you memorize quite a few of them. I don't believe in memory because one day after this class is over, you'll forget. So why spend the time memorizing when you have a smartphone? So anyway. Okay, so how many electrons did that aluminum lose? 3. Okay, so we have a +3 and 3 minuses, so that's balanced. So this nets so each side nets 0 charge. Okay, so what else is going on here? Well, we have iron sulfate. So what's going to oxidize, the iron or the sulfate? That sulfate is SO4. Well, the metal is what's going to oxidize or reduce. The anion sulfate just kind of rides along and has no change. So we're going to ignore the sulfate for now. So we're going to have iron and, okay, up here, this is oxidation. So what's this here? Reduction. Remember, they have to go together. Reduction means you're gaining electrons. How many electrons do we have to gain here? 3. And if that happens, we're going to end up with iron metal. Okay, so is this net zero? Is 3 the same as 2? No. So what are we going to do? How can we fix this? Remember we were balancing equations and we had a 2 and a 3. What did we do? Yeah, so we're going to have like a lowest common denominator kind of deal. Okay, so if we multiply this by 3 and this by 2, and the iron over here is going to be 3. So now we have net 0. Plus 6 minus 6, 0. Yeah. Now, again, these are half reaction. This is what's really going on underneath the covers. Electrons are moving around. And the other way to look at this is we ignore all that and just say the metal's got to be higher. Well, that doesn't really tell you what. Wow. Okay. Now, when we add these together, what must we do to the oxidation side? Okay, on reduction, we need 6 electrons. 2 times 3, 6, right? So in the oxidation side, we need 6 electrons also. So what do we do? Multiply everything by 2. We have 6 electrons being given off, and we're receiving 6 electrons. Okay, 2 times 3, positive 6. 2 times 3, negative 6. So we have net 0, both sides. Okay, so let's add these two together. Now, important here. How many FEs do we have on the bottom? Yeah. Down here in the reduction side, we have 3, right? How many sulfates? How many sulfates? How many SO4s are we going to have to go along with that? 3. Yeah. So the iron and sulfate is a 1-to-1. If we have 3 iron, we're going to have 3 sulfates. So in the end here, when we tally everything up, we have to make sure that the sulfates also balance. Okay, so we're gonna have another little wrinkle here. Let me bring this up. Oops. Okay, so here we have simplified reaction. 2 aluminums, 3 irons, 2 aluminums, 3 irons. What changes is the oxidation state. The charge changes. That's it. 0 plus 3. Okay. All right, so what do we got going here? First of all, is this reaction going to happen? So we look on the left. Where is aluminum? Aluminum's a metal. Is it above or below iron? Okay, aluminum is above, so that reaction is going to happen. However, when we write this reaction, that's the simplified reaction. This is, we have to include this reaction here. We have to include the sulfates. Now notice the sulfates go through that unchanged. Ions that don't change are called spectator ions. So sulfate a spectator ion. Spectator ions. Think about a basketball game. When you're a spectator, you participate in the game? No, you watch it. So you go into the game at the beginning and you end the game at the beginning or leave the game at the end, and you're not changed. Of course, you might be happy or sad, but you're not changed. Okay. If you're a spectator ion in chemistry, this ion is not changed at all. It just goes through unscathed. There's an ion, wait, there's a. Okay, so we have the spectator ion sulfate here. We have to deal with that. So how many sulfates do we have on the left? Okay, this says right here, we have 3 iron sulfates. So how many sulfates do we have? 3. We have to have 3 on the right. Right? So the problem is what's the charge on aluminum? The charge in sulfate. It's 2. Here we go again. So we have to balance out. So if the sulfate's going with the aluminum, charges have to balance. Okay. So how are we going to make this balance? How many aluminums do we need? How many sulfates do we need? What's the common denominator? What's the common denominator between 2 and 3? 6 again, right? So we need 2 aluminums. Three sulfates. That's 0 again. Now that's an ionic compound. Ionic compounds in a solution don't exist together. They're just kind of floating around independent. It's kind of a next week topic on double replacement reactions. And I'll talk about this tomorrow as well. Talk about more solution stuff. Okay, so this is what the aluminum and sulfate looks like on the right. That's why I'm writing it like that. Yeah.
Why does it have the thing?
It's on the right, bottom right. Okay. Remember, we have to balance the equation. Okay, so let's look here. In fact, let's okay, so this is what is going on here. Okay, so we have aluminum metal, ferric sulfate, aluminum sulfate, ferric metal. Now, in chemistry, we always balance things out. So we have the aluminum, we have the iron. I'm going to keep the sulfate together. So we have 1 aluminum on the left, 2 on the right. 1 iron on the left, 1 iron on the right. 1 sulfate on the left, 3 sulfates on the right. So it's not balanced. So leave the simple ones to last. So we're going to balance the aluminum and the iron metals last. So let's look at this here. So if we take and multiply this by 3, that's going to kick the iron up to 3 and the sulfates up to 3. All right. So is it balanced? No, it's not. Okay. So what can we do to change that? Okay. So we got 3 on the left, 3 on the right, 3 sulfates, 3 sulfates. Aluminum is a problem. What do we do about aluminum? Okay, now it's balanced. We've already checked whether this reaction is going to go, and it is, because the aluminum's higher than the iron. So this we're going to practice a lot in lab. You're going to be doing the reactions, and then you're going to have to write out the reactions. Now the problem in lab, this activity table does nothing about how fast those reactions are going to occur. That's called kinetics. That's a whole unit into 1B, whole unit, a biggie too. So kinetics has to do with how fast the reaction goes. It can go like this, or it can go like Pokey Puppy. That says nothing about speed, what we're looking at right now. Lab today. How can you tell a reaction happens? Color change, bubbles, solution could become cloudy or opaque. Those are all indicators a reaction has happened. And that means visible results, okay? There's a problem though. Sometimes it's no visible result. For example, if we take an acid and a base, mix them together, it appears like nothing happened. Now, if we did it in large enough quantities, it would get hot. Another indicator of a reaction happened, temperature change. But in the quantities we're working with in there, you're not going to notice it because we're working with little tiny things. So sometimes there's no visible reaction. So we'd write it as no visible reaction, NVR. Because NR means there's no reaction, visible or otherwise. But in lab, we have no way to know that, because we don't have any microprobes to check out the temperature. Okay? That's one deal that you're not going to be able to observe in there is when you have an acid and a base, is there a temperature change? And I'll tell you what the acids are and what the bases are. Okay, so we've done a lot. There's a lot of parts to that. And I cleverly okay, so are there any questions about what we did? Lots of practice. Now, if we go over to Canvas files. There's a couple more worksheets on practicing. Now, your lab itself has got a lot of practice. So that's what I really like about the next two labs. There's lots of practice on balancing equations and all that stuff. So it's really good. But additionally, I've got these other worksheets. Also, there is this one's double replacement, the net ionic equations. So that's practice as well. That would be for next week's topic. Same with this up here, net ionic equations. All right, so let's do some more practice. Okay, so what if we mix zinc metal and hydrochloric acid? Now, in the acid base unit or subunit, we're going to be talking about, remember that one lecture a little while ago, I talked about what is an acid, what is a base, and there's strong acids, weak acids, and no acids. Okay, we're going to be working with strong acids 99% of the time in here. In 1A and 1B, we'll be working with weak acids, which are much more complicated. Okay, but strong acids are much more straightforward, and that's what we're working with in here. You've got to understand strong down pat before you can even touch weak acids. Weak acids, they're very variable because some are stronger than others, and that comes into play. That's where the complexity of working with weak acids comes into play, or weak bases for that matter. Okay, so let's look at hydrochloric acid is one of the acids that we use frequently. So HCl is a strong acid. It means it completely ionizes to H plus and Cl minus all the time. There is no HCl present in a beaker full of hydrochloric acid because by definition, a strong acid separates, disassociates. Okay, so when we see that HCl, I want you to think of that. That's what happens in solution. Now, next Friday, I'm going to be talking about a little thing called AQ. AQ stands for aqueous. That means it's dissolved in water. Okay. All right. So does this reaction happen? Well, we've got H pluses now because we're dealing with an acid. So let's look at the activity chart. Okay, so there's the H plus there. Okay, and what was the other one? Was it zinc? Zinc. Okay, so where is zinc in relation to H2? It's above, right? Okay, so is this reaction going to happen? Yeah. If I can find it again. Oh, here it is. Okay, so this is going to happen. That means the zinc is going to go to zinc plus 2. I know that because it's on the chart. Now, what about these guys? Which is a spectator ion, the Cl or the H? Chloride is the spectator. So nothing happens to it. So we can ignore that for now. We're just going to look at an H plus. What does H plus do? Look on your activity table. About 2/3 of the way down. Is it H plus on both sides? Well, first of all, what is zinc doing here? Oxidize or reduce? Oxidize. So what must the H do? Reduce. So H plus goes to H0, right? However, H0 doesn't exist. It's H2. We need two of those. It's treated like a metal. It's sort of depends on what chart you're looking at as a metal or non-metal. But it's in this deal, it's treated as a metal because it's being oxidized and reduced. Okay, so zinc is above the HCl or it's above the H plus. That means this happens. Okay, so let's okay, so let's write the half reactions here. Okay, we have zinc. Okay, it loses 2 electrons because +2, that means it loses 2 electrons. So that's the oxidation. Reduction, okay? The reduction is it's not H, it's H2. That means we need 2 of those and 2 electrons. Just like in your activity table. Okay, so let's add these up. The 2 electrons cancel. Leaves us with zinc, metal, plus 2 H pluses. Now, H2 is a gas. As you all know, hydrogen gas. Okay. So is it balanced? 2 H's, 2 H's, 1 zinc, 1 zinc. Now we have to throw in the spectator ion, which was the chlorine. So how many zincs left and right? 1 and 1. 2 H's, 2 H's, 2 Cl's. So what do we need to put on the right? 2 Cl's. Now notice something here. Cl is -1. Zinc is +2. Is that a net zero? Nope, it's not. We need 2 Cl's, 2 -1s to balance the +2. So it's not zinc chloride, it's zinc chloride. 2 of them balance it out. Okay, so it's balanced now. So whenever we're working with acids now, don't think of them as HCl together. It's H plus, it's Cl minus. The other strong acid is sulfuric H2SO4. That's a little trickier because it's got 2 H's that come off. Okay, so, what's the spectator ion? What's the spectator ion? Chlorine. Notice I say spectator ion, so there's a charge associated with it. It's not Cl, Cl minus. Okay, so in this reaction, you're going to see bubbles from the H2 gas coming off. Okay, and the zinc is above the H2, so we know this reaction is going to go. Zinc is very prone to oxidation. Because it's high in the table. Okay, are there any questions about that last one? It was a little trickier because it's an acid.
States that does in our lab, solid, a liquid, how would we find that information?
Well, zinc is a metal, so you know it's, except for mercury. Mercury's not a metal. I mean, it's a metal, but it's liquid. That's the only one. So if it's a metal and it's got 0 superscript, it's a metal. I mean, it's solid. Now you can put an S there. Now, next week on a double replacement, we're going to have no metals. Any metals are going to be ions, but no superscript zeros. So again, single replacement reactions, 99% of the time, except when we're dealing with acids, are metal, solid metals. And sometimes the reaction will happen and some won't. Now, going back to when I first started talking about these. So if you have a metal that's low on the activity chart, it's going to stay in pretty good shape in terms of oxidation. So that's why platinum is expensive. Gold is expensive. And right now, the precious metals have jumped 300% and 400%. You guys know why? Because of tariffs. Because people are not putting their money in stocks anymore. They're putting it in precious metals, which tend to be very stable. They don't go up much either, except during crises like this. But everything will stabilize eventually. It always does. So precious metals are precious because they don't change in the atmosphere. So that means they're lower in the chart. You notice silver's at the bottom, gold is at AU, gold is at the bottom, platinum's at the bottom. Things at the top oxidize really easily. Yeah. Look at the bottom of your activity chart. Yeah, it depends on that. Yes, some people think, huh? PT. The precious metals are the ones that are in short supply. And the reason why they're precious is because they don't oxidize. Some don't oxidize as much as the others, like platinum. Right? You never see a platinum solution. You see platinum used a lot of catalyst, but never in a solution. Gold, you have gold solution. That means it's oxidized. Platinum is more stable than gold because you don't see it in solutions. Platinum is, I don't think it's all that attractive. I know one of my wedding rings, I've been married. One of my wedding rings was made out of platinum. I like the gold one better. I think it's more attractive. Now, gold is, remember we talked about solutions? I said gold is frequently mixed with copper because gold is very soft and it tends to wear. They put copper in to make it stronger, so it doesn't wear as much. And that's where the carat comes in. Carats is a index of how much gold is in there versus non-gold. Okay, well, that's what I wanted to cover on single replacement reactions. Okay, How are you guys? Feeling okay with this? This just takes a lot of practice. And I've given you that opportunity with worksheets, and then the lab itself is a lot of practice. Okay, so we will see you in a little while over there. It's a good lab.
Can I stay tomorrow for a lab? I have today, but can I stay tomorrow?
Who's your lab partner?
Last time he wasn't here, so I was with another girl.
Is your lab partner here today?
Yeah, I see him, yeah,
Okay, I want to ask him if he can come tomorrow too. It would make it,
but I think staying today. I saw his ring is like offered. I'm gonna
Tomorrow.
find,
tomorrow fine.
great, thank you.
I had love on Saturday, but I'm going to do it today instead.
Sorry, say again?
I was gonna redo my lab today instead. I have it scheduled for tomorrow. Okay, I know.
You can, this time of the semester, people have really a lot of room in the lab, so you don't even have to. Is your lab partner?
I've never had a lab partner. I've missed all of your labs.
Okay, well, we'll find one.
Okay, thank you.
Yeah,
I think I was here when you handed tests back. Last Saturday.
And that's.
you like few of the people. Yeah, just,
The lab due to one, you submit it on Canvas as lab 6. Not with Canvas. Already.
yeah, one of them, there was a week, even give 2 weeks. I try to make it a 1 week, a week from Saturday. Always do on Saturday
Yeah.
at midnight.
But there's nothing on Canvas. Because remember, it said last week that it was due last Saturday.
Yeah, I think, didn't I change that? Well, the trick is their name match.
Well, no. Okay, yeah, that's my handwriting. Okay.
The problem is you had to cut staple off,
Yeah.
and that's because of,
Did I get an 89? Wait, I actually got an 89.
Yeah.
Oh. I'm shocked. I didn't see. I thought I got like a 50. No, I'm surprised. Thank you. So I wanted to ask.
Is Malarity due tomorrow? I don't think so. I just want to make sure. So I like don't forget.
See, those.
check.
I did one.
I know.
I'm like.
Did a